हेलो। हेलो। हेलो।
Ready, ready? For speaker, this is the laser ka, ये pointer का. Oh, lovely. A pointer म्हणतो ना? नाही pointer ना? Nice. The speaker will use his own laptop, okay? Fine. We are ready. We just need your laptop. Apple, yeah, my friend. No, it's better.
You don't have like that.
Yeah, better.
I do okay. You can probably get sites.
We should have Wi-Fi, but which network we connect?
Like,
How will you have Wi-Fi?
another we can. Yeah, oh, there's no like.
But you have 5 by 2
Yes,
HDMI.
HDMI. Live streaming via Zoom.
Yeah, but if you please send to the projector, that's not a problem. I don't know. I can give you a better and it will transfer your problem.
No, that's very kind of very nice.
Animation will write us. But you have to Wi-Fi, will there? Okay. It's good. We can do. That those need power.
Hello, check. Check.
पण मला म्हणजे पण म्हणतात की you have to have the Mac on Wi-Fi. I'll call around myself from this. This is the time when everybody is Telegram will work? Does Telegram have a problem with this?
Yeah, I have really seen it says I'm connected.
Hey, Rahul, Rahul, we are in need of some urgent help.
So do you want me to try it now?
You are outside the PF, is it? ठीक है. हाँ, काय झालं माहिती का आमची development speaker जे
I'm
असतात
connected.
त्यांना PF वाटतो एक मिनिट नाही राहू it's okay एडिटर वर कनेक्ट केला आहे एडिटर वर कनेक्ट केला हां झालं बघ ट्रॅक करतो आता नसेल तर आम्ही कॉन्टॅक्ट केला
Do you want me to listen to that?
अच्छा
Zoom.
चालेल थँक यू
This question I am raising last week. No, I need to update my Zoom to.
That should be. Do you remember your preliminary topic of the week?
I don't, but it's always,
This is because of podcast and everything, but then it's this. So I haven't used YouTube and everything, but stuff.
distribution they directly contain in the segment. Because of this, but not in this.
But they.
Maybe it has to do multiple updates, like from 10 to 11. From browser tag it. Okay, yeah.
Empty correctly to audio.
Oh,
Hello, check.
Oh, yeah, fine, what? Yes. Okay. Now we just. Who will check the movie number?
oh, let me put
We have got 7 to 10 years. म्हणजे फोर आता टॉपिक के लिए है ना हमारे पास we can go we can bring in paper we are ready right yes कोई एलिजिबल I had sent a message to Jayara.
Check. Check. Check.
ठीक है, ठीक है, एक सेकंड। Don't mind having a seat.
Sure. Oh, you want me to sit there? Oh, sorry,
Normally
sorry.
we do that if it's such.
Sure, sure, yeah, yeah. And nothing much to, it's very normal. Dear siblings, or dear siblings, dear.
All right, everyone. Very good afternoon to you and welcome to today's Wednesday colloquium. First of all, I
thank Jyotishman sincerely for giving me this opportunity to host today's colloquium. You may want to know that Jyotishman is traveling and expresses his regrets for not being with us today. So first I'll introduce the speaker of today, and I found it to my surprise that a lot of people in TF actually know Manoj very well. But still, to those of you who do not know Manoj, it's a great pleasure to introduce Manoj to you. Manoj Prabhakaran is the Vijay and Sita Vashi Chair Professor in the Department of Computer Science and Engineering at the Indian Institute of Technology, Bombay. His research interests span theoretical cryptography, information security, and various topics in theoretical computer science and information theory. Prior to joining IIT Bombay, he was an associate professor of computer science at the University of Illinois, Urbana-Champaign from 2005 to 2016. He received a PhD in computer science from Princeton University in 2005. He has received an IBM PhD fellowship, an NSF Career Award, a Beckman Faculty Fellowship, and a Ramanujan Fellowship. He is an associate editor of the Journal of Cryptology, a member of the steering committees for the Theory of Cryptography Conference and the Information Theoretic Cryptography Conference, and a member of the ACM India Cyber Security Task Force. At IIT Bombay, he heads the IITB Trust Lab. Thank you very much, Manoj, to be with us, and I invite you to deliver your colloquium. Thank you.
We will ask questions in the middle there.
Yeah. Thanks a lot, Sushil, and thanks everyone for coming. Expecting a much sparser audience. So I should start with a disclaimer that I'm a computer scientist. I was told that a lot of the sciences faculty tend to be, sciences students and faculty tend to be in the audience. So it's about something related to quantum mechanics, but certainly this was not a physics talk. I don't know enough physics to give you a talk on that. We'll talk about two related notions in cryptography, post-quantum cryptography and quantum cryptography. And I intend to keep this kind of very high level, but let me start with an overview of cryptography as much as we'll need to know for this talk. Please feel free to stop me and ask any questions at any point. Okay, so at a very high level, there are a few different kinds of cryptography tools that we use, we all use in day-to-day life often. And I'm classifying them into symmetric key cryptography. I'll tell you what it is in a second. Public key cryptography. And these two are for tools for secure communication mostly. And the last thing there is secure computation. Okay. And these first two you use every day when you connect to the internet, HTTPS, all of that uses both public key cryptography and symmetric key cryptography in your system. So symmetric key cryptography refers to you want to do encryption, you want to do message authentication in a setting where the sender and the receiver both have the same key. They have a priori shared a key. Okay, so that's the symmetric part. They both have the same key. And encryption and message authentication are the two different tasks for which you would use these things. But that's not good enough for you want to log into or you want to connect to some website out there, Amazon or Google or whatever. You're not shared anything key with them ahead of time. Maybe you're going there for the first time. So symmetric key cryptography is not enough, and that's where public key cryptography comes. So the web server you're trying to log into or connect to already has a public key. And somehow your computer knows about it. Okay? It goes through again some certificates and so forth. But at the end of it, it's because there are these public keys that can be published that everybody is allowed to know that your computer knows about that server. And the server holds a private key, which is meant to be a secret, right? And you can use this for encryption. So only the person with the private key will be able to decrypt messages, but everybody will be able to encrypt messages to them. So that's how you would send encrypted messages to somebody with whom you have never shared a private key. You have shared the public key, their public key is public, so you can just use that to encrypt a message sent to them. Only they can open it, okay? That's encryption. Digital signatures is another thing that uses public key cryptography. I have a secret key that I use to sign produce a signature on a message and attach it to the message, anybody out there who has my public key can verify my signature. They can verify that the signature does correspond to this public key. So if they know that this is my public key, they know that this message was signed by somebody who holds the corresponding secret key, and that must be me, hopefully. Okay. And when you do HTTPS, you don't necessarily do public key encryption directly. You instead do something called key exchange, which is essentially public key encryption. You use the public keys of one party, let's say, to talk to each other and establish a symmetric key. And from that point onwards, you use symmetric key cryptography because it's much faster. Okay? So that's kind of what you encounter on a day-to-day basis. So these are basic applications of cryptography, all about communication. But there are also advanced applications which broadly fall under, you could think of them as secure computation. Some of you may have heard of some of these terms. Zero-knowledge proofs, kind of fascinating concept to convince somebody of something without telling them why it's true. Zero-knowledge proofs. Secure multi-party computation, which kind of goes further, and it's not just about verifying some validity of some statement. It's about computing some function on inputs that are distributed among several parties without revealing to each other your private inputs. You get the outcome of the computation. The input to the computation will be kept private. Okay, so that's secure multi-party computation. You might have heard of terms like fully homomorphic encryption, which also fit this general idea that you want to compute on data without really knowing what that data is. It's kept encrypted. Good. Okay, so there's a lot more here, and this is pretty much where a lot of the action in theoretical cryptography is happening today. And for a long time, the basic applications were you could say, stabilized, which was all about engineering, getting things to be faster, and so forth. But of course, things have changed recently, and there's a lot more interest because of post-quantum cryptography, which I'll talk about in a second. Okay, but before going further, where do these, what's underlying all these cryptography tools? So you need to use computational hardness to get, say, something like this public key cryptography, where anybody can encrypt, only the person with the key can decrypt. It's magic, right? It's computational magic. How is that possible? And that's possible because there are these functions which have certain properties. For instance, there are functions, there are one-way functions, which are easy to compute in one direction. It's easy to compute the function, but it's hard to invert it. Okay? And that's computational hardness. Without this kind of computational hardness, none of this will be possible. I shouldn't say none of it. Some of the applications are still, they do not require computational hardness, but for our purposes, everything that you do in cryptography today on a day-to-day basis is based on computational hardness of one kind or the other. And there are different kinds of computational hardness. Okay, so at the top, symmetric key cryptography is it needs a simple kind of computational hardness. So one-way functions is a prototype of that kind of hardness, right? What I already mentioned, you can compute easily in one direction, hard to invert. To do public key cryptography, you need to go a little further. You need functions with a little more structure and a little more, so you need trapdoor functions, something which they're again one-way functions, but there is a trapdoor, and if you have the key for the trapdoor, you can actually invert the function efficiently. And that'll let you do all sorts of public key cryptography. But if you want to do secure computation, you want to go further. And one of the things that you would need is something called oblivious transfer. I'm not going to describe what it is right now. Probably mention it later in the talk also, because it has a quantum cryptography connection. Okay, but that's suffice to say, it's a stronger kind of computational hardness. Okay. Now, the thing about computational hardness is that, unfortunately, we don't really know if these things exist, if computational hardness exists in real life, in mathematics, right? And the reason for that, we think it does. We think a lot of functions are one-way functions. We don't have any algorithms for, we can efficiently compute in one direction. People have tried, but haven't found any algorithm to go in the other direction. So that would be a candidate for a one-way function. The reason why we cannot prove that it's a one-way function is because there are even more basic questions we don't know how to prove. For those of you who have heard of it, P versus NP, P not equal to NP is a conjecture that there are problems for which it's hard to find a solution, but it's easy to check a solution if you give me one, right? That's a P not equal to NP conjecture. We are nowhere near being able to prove that fact or prove that. So it's a conjecture, right? That's all we can say right now. Now, just because mathematicians have not been able to prove these conjectures doesn't mean we will not use them. There's very good use that we have from cryptography. So what people have done is just go ahead, make those assumptions and use them. If we are proven wrong later, we don't expect to be proven wrong later, but if something like that happens, we'll worry about it then, right? So we are not going to sit around and not use these tools just because we are not able to prove that they are not secure. But of course, we do it in a principled way. We just make a few assumptions, state them properly, ask people to try and break those assumptions, and then base everything, the security, on those assumptions. So we do give proofs of security based on those assumptions. Okay, so these are the different levels of hardness. As you go down this list, it's a stronger assumption. We are asking for more and more exotic kind of hardness, and it's simpler to assume, or it's easier to believe things on top than things at the bottom. And roughly, you could say the things at top are talking about hardness of functions, unstructured function. They're just hardness. If you pick some random, reasonably defined random function in a way that it's still easy to compute in the forward direction, the conjecture seems reasonable that it would be hard to invert. Okay, so that's kind of unstructured hardness that you need for one-way functions. That doesn't suffice for trapdoor functions. You need some algebraic structure, some clever, trapdoorness there, right? So it doesn't come out of, if you just put things randomly together, these trapdoors don't show up. So, so those things are more assumptions about more structured objects. So we have a lot of candidates, algebraic and number theoretic and so forth. Of course, there are, this is roughly the top things. Symmetric key cryptography needs one-way functions, public key cryptography needs trapdoor functions, secure computation needs oblivious transfer. Is the general rule. There are exceptions. Digital signatures can be based on one-way functions. Okay.
We have a point.
Sure. Yeah. Yeah. So digital signatures can be based on one-way functions. So it turns out, though we don't do it in practice because it's inefficient. So we actually do use the these kind of public key assumptions to build digital signatures. Zero-knowledge proofs also, it turns out, can be based on one-way functions. We don't do that in practice. So there's a lot of practice of zero-knowledge by now, and they do use more structured assumptions. Okay, but we'll forget that. Okay, so going on with the landscape. So these are the kind of computational hardness we want. Where do we? Where do we get them from? We get them from various mathematical problems that people have studied over a long time. Well, mathematical candidates as well as ad hoc candidates, ad hoc designs that have been put together to resist all known attacks so far. So symmetric key cryptography, you would hear about things like block ciphers and stream ciphers or hash functions. And there are some very well-defined properties they need to satisfy. And there's been a lot of literature on how to show that something doesn't satisfy those definitions, right? Attacks on them. And yeah, so these are, you could say, ad hoc or complex constructions, and they seem to have withstood the attack so far, the current candidates. For public key cryptography, where you need more structure, they're not just some ad hoc constructions. You carefully, use number theoretic or algebraic structures. And there are two prominent candidates that were discovered in the 70s. So RSA by Rivers, Shamir, and Adelman, and Diffie-Hellman by Diffie and Hellman. And they use algebraic or number theoretic structure. And in some sense, it's not just two arbitrary, two kind of, candidates out of nowhere. They seem to be somehow very, like they're truly the things you discovered. So what I mean by that is they were both discovered in the classified work of at GCHQ. This is the British intelligence agency. In the 70s, early 70s, before they were discovered in the open literature by RSA and by Diffie and Hellman. It's exactly the same constructions, right? So Cox discovered RSA first, and then later Williams discovered Diffie-Hellman, and then later they were discovered in the open literature. And this happened in the 70s, and till now they are our most prominent candidates for public key cryptography. There have been others, but not as popular or well understood as these two. Okay, so these are somehow very good candidates. And this is what you use when you use HTTPS.
Was it in the context of secure communication?
Yes, yes. So
Okay, I'm going to ask you to repeat that for the audience on the net.
Okay, good.
Sorry.
Yeah, no, so I was asking that were these discoveries made in the context of wanting a way to do secure communication or completely different?
Exactly for that. So public key cryptography was invented by Cox, essentially, and RSA was the first, construction of public key cryptography. It was for exactly this purpose.
But in this, you said 70s. Like
It was in the 70s.
there wasn't really any real internet or networking going on at that
Military
time.
always needed communication.
okay.
So telegraph or whatever, right? It's over the, so military has been the biggest driver of secure communication starting from the World War time. Okay, so this was called keyless encryption. I mean, there's no shared key ahead of time. Okay, so that is great. But unfortunately, in the 90s, people discovered quantum computing algorithms that break both of these candidates, okay, RSA and Diffie-Hellman. Diffie-Hellman comes in a couple of flavors, number theoretic or elliptic, something which is more algebraic, called based on elliptic curves, and they are all broken by these quantum algorithms, okay? So, but before I let me also jump ahead and tell you that things are not all bleak. There are other candidates. They're just not as popular or prominent, but there have been other candidates all along as in since the 80s, based on other structures. So codes, error correcting codes, multivariate polynomials, and lattices. Okay, so some mathematical structure. And these currently, as far as we know, are immune to any quantum algorithm. Just as we think they are immune to classical algorithms unless you spend enormous amount of time to break these things, right? So there are no realistic classical or quantum algorithms known that break these crypto systems based on codes or lattices or multivariate polynomials, and these are what form the basis of post-quantum cryptography. So post-quantum cryptography or quantum-resistant cryptography refers to schemes which are still standing even if quantum computers become large-scale quantum computing becomes real, right? There's one more thing. Yeah.
It's a naive question, but we hear of these high-profile systems getting hacked. Is it because somebody solved a hard problem and gotten
No,
lucky, or
yeah.
it's always
Not
something
at all.
else?
Yeah. So there are many other problems than in communication systems or in computer systems beyond cryptography, and those are the weak links.
Not never because of this.
Yeah, it's never because of this, unless there have been instances where this was done, implemented wrongly, something was not random when it was supposed to be, and those, yeah, then cryptography has been attacked. Those.
Yeah. We did not know that everything we directly was followed and
Actually, I couldn't hear you. Maybe.
Okay, one second. Good that you didn't hear him. I need you. I need to get the mic to you. Can I make a request to people? If you have something to ask us, say, raise your hand. Be patient because the audience on the net has to hear.
So there was one case with roughly of the following kind, that it was known for a while that a certain length of RSA was breakable, even just on a desktop, with some maybe a few days of computation. But many prominent websites were still using it, and someone, just to show that this has happened.
Yeah, so there have been, yeah, you're right. Like Peter said, there are a lot of situations where things were known to be, there is a bad way to do it, and people knew it was a bad way, and that's how it was still done. And there are also instances where, so RSA is based on hardness of factoring. I'll talk about this in a second. But turns out there was some lack of randomness in various systems. So a lot of these independently generated keys using this library turned out to share common factors. And then you can find them just by GCD computation. This is a fast algorithm. And you can discover a lot of public keys out there that people are using. Just scour the net and try doing GCD computation, and you can find factors. Okay, so there have been errors in the implementation. Things were not random enough, and things got broken because of that. But the first the most significant bit here is that classically these are all good assumptions as far as we know. They're not broken. No cryptographic system has been broken because of these assumptions being wrong.
Sorry. I say this at every talk. Repeating here again. You say it's a good assumption. It's not always. But depending on who you talk to, it is. I would say it's a bad assumption, right?
And
prime factoring, because there's no complexity theoretic reason to. There's no evidence whatsoever, apart from the fact that we have not been able to solve. There's no theoretical evidence to suggest that factoring is hard.
That's in fact true. That's not just true for factoring, that's true for symmetric key cryptography also.
Sure.
And that's true for elliptical cryptography also, right? So indeed, these are assumptions, right? And the only reason we go with these assumptions that they are not being shown to be wrong yet, and they get us so much value. Okay, so let me, I'm already kind of running behind time, but yeah, I can cut down on things later in the talk necessarily. There's one more candidate which would stand, which is to use quantum communication for cryptography. Okay, so this is kind of, you could say the other side of quantum. Quantum, instead of being the adversary, quantum is now helping us. So using quantum communication to do cryptography. So that's another candidate, but it's not as straightforward as it sounds. So I'll come back to that in the second half of the talk. But let me start with, I mentioned quantum attacks. So what are they? So quantum computation started off as a theoretical model for computing. You manipulate photons or other things which can encode what I call qubits, and you do measurements, and you do a bunch of transformations and then measure. And turns out you can do useful stuff with that, right? So that's quantum computations theory started in the 80s. And now it's a very big deal. There's a lot of, it's not just theory. There's a lot of interest in making this practical. And there are a large number of, techniques by physicists and, some of people here, I guess. And it is feasible today, okay? But in rather modest scales. or for very specialized tasks. The big deal about, or the big interest in quantum computing came from the fact that it's actually this, cryptography being broken is the main driver behind the interest in quantum computing. So in the 90s, in 94, Peter Shor came up with an algorithm for breaking to factorize the product of two large prime numbers. So that's the integer factorization problem. You pick two large prime numbers, multiply them. Okay, that's a very easy thing to do. But it's a one-way function. It's hard to invert. It's what it looks like. Okay. Of course, for all that we know, it's not true. There might be a classical algorithm, but none have been found. Shor found one, but in the quantum computing model. And it's of course a big deal, but it was a theoretical deal, right? There's no threat for. There's no chance of quantum computers being built at that time. So it probably stayed like that for a while. But actually, Shor's algorithm not just works for factorization, it works for the Diffie-Hellman cryptography also. So it can solve something else called the hidden subgroup problem. And it's essentially the same technique, same algorithm. Okay, so there are other algorithms also which are based on Grover search, which is not as dramatic as Shor's algorithm in terms of the computational speed up you get, but still it can be used to reduce the level of security of symmetric key cryptography. From what we believe, is currently, I think of a brute force attack is pretty much the only thing you can do on this particular hash function or block cipher or whatever, and you could use. If you have a sufficiently large quantum computer, you could do it a little faster using quantum computing. Okay, so there are algorithms for that. And very recently, if you have been following the news, you might have heard of an algorithm by Oded Regev. It's a breakthrough algorithm. It's a different way of doing integer factorization. May or may not be, practically impactful. Shor's algorithm has seen a lot of optimization engineering-wise, and Regev's algorithm I'm sure will see those kind of optimizations. Already people have been doing some. But the big picture is that it's just another algorithm doing essentially the same thing Shor's algorithm was doing, but it's different. So these are the attacks we're worried about, right? But before I make you panic, I want to kind of put things in a little bit of perspective. That current quantum computers are not a threat to current cryptography. Okay, so they are far from doing that. In fact, if you look at, to give a comparison, if you look at classical computers, the best known, the record for integer factorization is breaking an 829-bit challenge, and original RSA challenge. So breaking factorizing an 829-bit number into its two factors. And this was in 2020 using a humongous amount of classical computational power. Okay, so big supercomputers. This is not considered a threat to 2048-bit RSA, which is kind of what is recommended by most of the software today. Because you might think, okay, 829, getting close to 2048. Not really. Every 2 or 3 bits you add, you're doubling the amount of resources that classical computer needs. The system that was used to break this, to do this factorization, you increase the size of the number, size of the challenge by a few bits, the required resource doubles. And there's a lot of bits being added from 829 to 2048. You double that many times. It's nowhere near a realistic concern. On the other hand, using quantum computation, what do we know practically implemented? I may be missing very recent references. A lot of my references from Wikipedia, so you can probably do better than that still. Apparently, Shor's algorithm implementation of Shor's algorithm itself is only known for, this factoring 21 as 7 times 3. That's the best. But that's from 10 years back. So presumably people can do better. People have not reported it. There have been a lot of optimizations also. So I'm sure it's much better than that. But, nothing that I could find. Time to time, you keep hearing about other records. In 2017, using something called adiabatic quantum computing, a challenge of about 20 bits, number that's 20 bits long, was factored. Recently, last year, December or so, I think, there was a result announcement of breaking a 50-bit or close to 50-bit number using something called QAOA, quantum approximate optimization algorithm, and a lot of classical computation, right? And so these are, I want to point out that, these are.
Sorry,
not necessarily-
Manoj, the adiabatic quantum computing it's a new algorithm? Because I didn't think you could implement Shor's algorithm on an adiabatic quantum computer.
No, the thing is, the new algorithm. Okay, they're not using Shor's algorithm. Only Shor's algorithm, record that I could find as very small numbers, right?
Right.
The thing is, okay, two things. First is, as of now, no danger, nowhere near 800 bits or anything. Secondly, you might think because they're getting bigger 50 bits, they're not using Shor's algorithm, so they're using algorithms which are also going to scale badly. Okay, they're closer to the classical computing algorithm than Shor's algorithm. But Shor's algorithm itself is what we are, or Rege's algorithm is what we are concerned about. They do scale very differently. They scale polynomially instead of exponentially. Okay, so you add a few bits, it's only going to, it's not going to double the amount of time it's going to take. Okay, so that's a concern. Over time, we could use Shor's algorithm or something like that, Rege's algorithm, for instance, and use reasonable sized quantum computers running for reasonable time to break really large crypto systems. Okay? But as of now, we are not near that, but why not prepare for that? And that's what post-quantum cryptography is all about, also called quantum resistant cryptography. And we already have some candidates. I already mentioned the first slide. And the main candidate nowadays is lattice-based cryptography. And a lot of cryptographers are interested in this, not because it's post-quantum candidate, but because it has a lot of other cool properties and gives us secure computing applications which otherwise we don't know how to do. Okay, so that's a prominent candidate, and I mentioned these others also earlier. But a word of caution: last year sometime, there's another candidate, or there's another line of work, something called isogeny-based cryptography, again based on elliptic curves and so forth, but very different. Was not considered vulnerable to Shor's algorithm. Okay? But it turned out, at least the main variant of that could be broken just classically. So forget quantum computers becoming realistic. It was broken on a laptop. So the word of caution here is that candidates for post-quantum cryptography tend to be much less studied and understood than things that have been around longer and much more carefully looked at and by more people. So there's a thing to keep in mind. These candidates may not even be classically secure. Okay, so if you're a user or an industry person, the short kind of takeaway is that post-quantum cryptography is for the future. When necessary, standards like TLS is what HTTPS uses. They will be updated with the PQC candidates. Okay, there are already some standards for lattice-based cryptography, but they're not part of TLS. And as and when those things are available, you just need to make sure you can switch your software, your products to using these standards, the new standards, and rather than the old standards. Don't try to do your own thing at this point. And there's one exception, which is if you want long-term secrecy. If you're interested in encrypting something or communicating something now, which you think has to stay secure for the next 20 years or 30 years, you might want to already use something which is post-quantum secure. What if the adversary is storing all the communication right now, and when quantum computers become powerful enough, they will break your message, break open your message. So if you're worried about that, you should try to use post-quantum candidates, but use them in combination with the current standards, maybe with a bigger key, because for all, as I said, post-quantum candidates are not as well understood. Okay. All right. So that's all I wanted to kind of say about post-quantum cryptography. So unless there's a quick question, I'll switch gears and move to quantum cryptography. Yeah.
Yeah, Manoj, so the last point you said that the post-quantum are not well understood. Does it mean that, unlike the RSA where there is a proof of hardness?
No. It's one
because even,
yeah, they are both heuristic in some sense, right? They're both assumptions. It's just that more people have worked on integer factorization compared to people working on lattice-based assumptions.
Okay, so it's
the
sort
mathematical community who has looked into it is much bigger in one case. Yes. Okay, all right. So switching gears, quantum cryptography, something very different. And here we are using, it's here. Quantum is our friend. You want to use basic elements of quantum computing, but much simpler and cheaper elements needed only for quantum communication and very minimal computation. And to do that, and to use that to do secure communication and maybe more. Okay. And the most common application that you would hear about is what's called quantum key distribution. And that's the main application. It's a mainstream application in the sense that it's commercially available. People sell it, you can buy it. You do need a quantum communication channel to use it, but you can buy the boxes which sit on either side of that channel. So what is it and where did it come from? And why do we need it, right? The original motivation of quantum cryptography is, if you want to be really paranoid, you don't know any of these, cryptography assumptions you're making are going to actually be true, right? P not equal to NP on my functions. But, whatever you're assuming, they're assumptions at the end of the day. And if you don't want to base your security on unproven assumptions, maybe there's another way you could use physics to get your security. You could use quantum, laws of quantum mechanics. So I mentioned computationally unbounded adversary. So that's a model. You're assuming that the adversary has all the computational power it needs, not just quantum computers. They can do unbounded computation. And still, I want security. Okay, that was the original motivation. There is a caveat, which I'll elaborate on towards the end, that you need an authenticated channel. It's a classical channel. You also need a quantum channel, but the quantum channel is not authenticated. So when I send a message, send a qubit, send a photon through this quantum channel, the adversary can intercept it, do whatever it wants with it, maybe send another photon to the other end, right? They can play man in the middle. So that I'm not making any assumptions on the quantum channel, but there needs to be a classical channel between the two parties, which is authenticated. The adversary cannot tamper. It's public. The adversary can see what's going on, but it cannot tamper with the message there. Okay, and we'll see that as some consequences. Okay, if you what QKD gives you, so QKD for quantum key distribution, there are many protocols. What it gives you is among other things, it's a post-quantum cryptography candidate. Right? It's going to be secure even against computationally unbounded adversaries, so certainly against quantum computing adversaries. Just want to give you a flavor of what goes on in QKD. So I'm just going to sketch a little protocol. Let's see how much time I'll take. So Alice and Bob, want to talk to each other over open channel, public channel, and end up with a key, meaning a secret string that they both agree on. So uniformly random string, such that an eavesdropper, an adversary, has no idea what it is. Okay, an eavesdropper who can also tamper with the quantum channel. So this will involve a quantum channel, and they're just what you're communicating are some physical things like polarized photons that encode a message depending on its polarization. So you need an optical channel or maybe through the air. And I'm going to show you this little protocol which uses the very basic principles that we all have heard about from high school about quantum mechanics. One is that if you measure a quantum system, the measurement itself can alter the system. And another is no cloning, which essentially says you cannot make a copy of an unknown quantum state, right, without destroying it. We don't need any quantum mechanics or the maths. Today, I'm just going to use a metaphor to talk about this protocol. And the metaphor comes from, or what it captures is this idea from Weissner in '68. It was published much later, called conjugate coding. And he was thinking of actually, this was the first application of first quantum cryptography result or idea. And that was actually motivated by having cash or quantum money. Okay, but what this, so I'll tell you what it, I'll use a metaphor to say what it is. It doesn't exploit all possibilities of how quantum states are used. It doesn't talk about entanglement, which is is something that is used in quantum cryptography, and doesn't talk about anything else. But it's enough to understand what's going on in this particular protocol, which I called BB84, Bennett and Brassard 84. Okay, so here, what you're sending through the quantum channel, what I call qubits, are just cards. Okay, they're cards. They come in two colors, red and blue, and they can have a bit, 0 or 1 in them. Okay. Now, the only thing you can do with this card, you look at it, you can't even tell its, you can't tell its color, you can't say what bit it is, you have to put it into a card reader to find these things out. Okay? And the card readers also come in two colors, red and blue. There it's a red card reader, blue card reader, you know that. But when you get the card, you have no idea until you put it into the card reader. Okay. Now, if you put a blue card into a blue card reader, it will work correctly. It'll tell you what the value is. And same for red, right? But if you get it wrong, if you put a blue card into a red card reader, two things happen. One is that it'll report a random bit, irrespective of what the original value is. Secondly, it'll turn your card into the reader's own color. Okay, so blue card will become red if you feed it into a red card reader. And the value in the card also becomes whatever it reported. So now if you took this card out and put it into the red card reader, it'll keep telling you the same thing. Okay? And in some sense, you have no idea whether you had actually put in a red card and it was always reporting the same thing, or initially what you put in was a blue card, which then turned red with a random value. Okay, so is a model clear? So this is the equipment we have, cards and card readers. You can give cards. How do you send cards? You actually give it to an adversary who takes your card and gives it to the other side. Okay, so at that point, they could do whatever they want with the card. They can read it, measure it, try creating another card. But of course, they can also only measure it by putting it into their card readers. So that's the only thing you can do. So that's our metaphor. Let's see the protocol itself. So first, remember the goal, Alice and Bob are talking in the clear, in an open channel, but they want to end up with random bits at each side. that an eavesdropper doesn't know. Okay, the first thing Alice does is it will prepare several cards with random colors, so uniformly random colors, blue or red, and uniformly random value, 0 or 1. And then sends all these cards, big stack of cards, to Bob. Bob will, what can you do with the cards? He'll just take all the cards and read them. He doesn't know what's the right color of the card, so he'll just read them using random card readers, right? So every card you'll randomly decide whether to use a red card or a blue card. And when I say random, I mean uniformly random. And then, after making all these measurements, he tells Alice, I've read everything. I'm not telling you the values I got, but I'll tell you the color of the card reader I use for every card. Okay? So card 1 is blue, card 2 was red using a red card reader, and so forth. So he sends all of these things. And Alice will say, actually, here is a list of the actual card colors. Okay? So these communications in the brown, they're classical communications, but over the authenticated channel. Now, Bob sees this and he realizes a bunch of those readings were done using the wrong card reader. There's nothing useful that you have from those readings. They turn the value, he got random bits from that. So he'll discard all of that. Alice also knows which ones were wrong, right? Because Bob told her. So both of them will say, okay, those cards are useless. Let's work with the remaining cards in which they know, Alice sent a blue card, Bob read it using a blue card reader. Of course, there's a chance that somebody in between took that blue card, changed it, instead sent the red card and so on. Okay, but let's ignore that for a second. So if nothing like that happened, then Alice and Bob would have got the same value. The value that Alice put in will be the value that Bob gets out. But they're going to check that, right? Because they don't know if there is an eavesdropper. So they're going to check if an eavesdropper has been changing cards. So they're going to check for consistency, and they're going to do this using sampling. They don't want to completely check this by opening up everything and saying what happened, because then they will not have any secrets to use. So they will just do a little bit of sampling. So Bob will pick a random subset, say even half, but could be smaller, of the undiscarded cards, and tells the values he got. Tells Alice, look, these are the values I got. Okay. And Alice will check if all those values are correct. If any of them is wrong, she would say, let's abort. There is an eavesdropper in the middle, tampering with our thing. We are going to abort. Now, you might wonder, this is not good enough. An eavesdropper can make them abort. Well, an eavesdropper could always make them abort if they just the quantum channel is in their hands. If they just do a denial of service, they refuse to send anything, or even replace everything that's been sent. They could have done a denial of service. So denial of service is not an attack. An attack is if Alice and Bob end up with keys. They think they got keys, and Eve knows some of that. Key, right? The key is not uniformly random. That's the attack. So Eve forcing them to abort. Eve is the eavesdropper. Eve forcing them to abort is not an attack. Okay, I mean, it's a denial of service, but it's not an attack on the protocol security. So if any value is wrong, they will abort. So if no value is wrong, what are we left with?
I'm sorry,
Then very
small question. So they exchange a large number of qubits, right, for verification.
yes.
So you're saying even if a single qubit is wrong, they abort?
Even if so this is coming from a practical question, because even if there is no actual attacker, sometimes qubits flip. So the presentation here is assuming only reason to flip is because there is a malicious attacker.
Okay.
Otherwise, you can put a threshold, saying if you see beyond the threshold, you will abort.
Okay, thank you.
But yeah, let me carry on with the original kind of setting where the only reason for a flip is an attacker. So at this point, what can we ensure? We cannot ensure that Alice and Bob, that there was no tampering. Maybe all Eve did was pick one card and tampered with that. And when either the tampering got lucky, like it resulted in the same card as that was being sent, same color and value, or that tampering got lucky in the sense that it was not picked in this random subset that was sampled to do the checks, right? In either case, Alice and Bob will be unaware of the attack that happened. And so it's possible that Eve knows a few of those cards, or that on a few of those cards that Alice and Bob think they have got the same value, they actually have different values, and they don't know that. But this can happen only in a small number of places. If it happens in a large number of places, with overwhelming probability, this check will find it and discard it. Okay. But these raw keys are not good enough for secure communication. You need good keys, which are, and there is a two-step process to make them good. Good means first you need to do reconciliation. So Alice and Bob need to make sure they have every bit that they have with high probability is the same. Okay, and for that they will do an interactive protocol without revealing everything. Of course, they will send some sketches, some hashes of what they have, and checks and isolates where things are not correct, discards them, and so forth. So they do some interactive protocol, that's reconciliation. In this process, they reveal more information to an eavesdropper. That's okay. So at this point, the adversary might have some information about the key. The next step is what's called privacy amplification, which is essentially, again, some sort of a hashing, such that the adversary, knowing a few bits is of no use. After this hashing, it knows nothing. Okay, it's called a randomness extractor in computer science. So that's privacy amplification. Okay, so this works. Let me tell you a little bit of, so this works in theory. In practice, people started implementing it right away from the 80s. So it was implemented in IBM research in 89, a very tiny 32 centimeter free air quantum channel. And there's also this anecdote I've heard. They had a big side channel attack, which is that these devices, they say these devices were secured as long as the adversary was deaf, because they make very different sounds when they're encoding a 0 and a 1. But anyway, so it was an demonstration of this particular protocol. It was implemented in a much bigger network, much longer channel, 23 kilometers, and later 400 plus kilometers in Geneva. There is a live network in Boston, in DARPA network between BU, Harvard, and BBN Technologies. It has some wireless links, some optical links, and there's another one that is there in Tokyo. And the most recent kind of famous one is there is an Earth space QKD from Earth to a satellite, Chinese satellite. And so it's a long distance, but of course it's just a straight line communication. So this was in 2017. Okay, so it's kind of real quantum QKD. There's a lot of actual investment into this. But let me take a few minutes to actually, how am I doing on time?
You said 2 minutes only.
I could, how many do I have?
10.
10 minutes? Okay, that's good. Okay, so let me tell you a few. I'll stop whenever I run out of time. But I think I'll stop. I can finish in 10 minutes. So let me go back to this caveat, which is that it needs an authenticated channel, right? So how do you get this authenticated channel? So remember, the reason we have quantum cryptography is we don't believe in, we don't want to believe in computational assumptions, hardness assumptions. So we cannot use cryptography to do this authenticated channel. Nevertheless, even if you don't use cryptography, you can do authentication in what's called an information theoretic sense. So information theoretically secure authentication. But you need to start with a short key ahead of time, shared key. Okay, and then you can keep replenishing it because this QKD will generate more key at each end. So you can keep, this information theoretically secure authentication consumes the key. You cannot reuse it, but you can bootstrap from it because QKD will give you more keys, so you take a little fraction of that and use that for authentication. Okay, so that's one way to do it. That's what BB84 was thinking, right? You don't need any computational hardness, just need a little shared short key ahead of time, and then we have this secure communication channel without computational hardness. But there is a reasonable question: if you have, where does shared key come from? And if you had it, do you need QKD? The whole point of QKD is key distribution to generate, shared keys at the two sides. So having the small key on either side is small, but still it's, how does it show up, right? And it's not a very, simple answer. So I sat down and kind of tried to make a little table of when would QKD be reasonable. And my table here has, on one side you have, so this is the kind of different cryptographic assumptions you are willing to make. At the bottom here is what BB84 originally thought of: no cryptography, no computational hardness. This one here is, there is cryptography, but everything is broken by quantum computers. Here it is, quantum computers break public key cryptography, but symmetric key cryptography remains post-quantum secure. And at the top, we have post-quantum cryptography. Even quantum computers cannot break that particular kind of cryptography. And not RSA or Diffie-Hellman, but say lattice-based. So that's this axis. On this side, you have different beliefs you have about a different kind of adversary you want to handle in terms of their quantumness. So this is the classical adversary, and this is a quantum adversary. In between, I have put in this future quantum adversary, which is, today there is no quantum computing, or it's not fast enough, whatever. But maybe in future, quantum computers will be there. Okay, and so that is this future quantum, and you want to protect against an adversary who is, kind of banking on that. And there are two settings depending on whether you have a shared key or not, right? And I guess there are two. C here means you can go with classical cryptography. You don't need quantum cryptography, and Q means quantum cryptography is the only way we can do things. Okay, so clearly there are things where you need quantum cryptography. The bottom BB84 setting with a pre-shared key, if you don't have any cryptography, any computational hardness, there's the only way to do, and it works against quantum adversaries, right? But this has a caveat, and the caveat is nobody would want to use this kind of cryptography in today's life, because to be information theoretically secure, you need what I call one-time pads. To send a 1 gigabit or gigabyte long message, you need 1 gigabyte long key. Okay, and of course, and to use QKD to generate 1 gigabyte long key will take a long time. It's very expensive. But on the other hand, movies are in gigabytes, right? So you do want to get that much key. So this is not a world you want to live in. This blue, where you need to use very long keys. It is light blue, and so things are a little better if you assume cryptography, which is if you assume only cryptography which is entirely broken by quantum computers. Not surprisingly, it will help you only in the world where there is no quantum. Oops. But it would, not be useful elsewhere, right? If you have a quantum adversary. I said it actually does help in the future quantum setting. And why is that? That's because authentication is like an at the moment kind of thing. So you use cryptography that will be broken by a quantum computer, but you use it for authentication, doing that authenticated channel. The fact that in future the adversary could have broken your authentication doesn't hurt you, right? The authentication is done and used already. So this will work. You don't need any post-quantum cryptography, but still it's a inefficient situation where the keys have to be really long. There's another cell here which is interesting, which is you only believe in symmetric key cryptography as being post-quantum secure, right? That sounds like a reasonable assumption. Against a quantum adversary, if you use authentication which only uses one-way functions, the thing I mentioned at the beginning, right? Digital signatures can be based on one-way functions. If you do that, and one-way functions are symmetric key cryptography, so then you are good. Symmetric key cryptography, if you assume is post-quantum secure, that's the only thing you're using as cryptography. So then you can use the quantum BB84 kind of protocols, and this would be good. This is not done in practice. The systems boxes that you buy, that I said you can buy, they don't do this, I believe, because this is very inefficient, the digital signatures. Right? But this is probably the way to go if you really think you have a quantum adversary attacking you. There's a little sweet spot here, which is probably the justification for using a QKD system today, which is you use digital signatures and efficient digital signatures which are not post-quantum secure for your authentication, but you only ask for security against a future quantum adversary. Okay, and that's also kind of reasonable today because we only have presumably future quantum adversaries. There are no current quantum adversaries. But this, if you are worried about eventually quantum adversaries will come in, then, which is what future quantum means anyway, then there's not good. You'll have to switch to the other solution. Okay. Of course, in practice, a lot of people believe we are in this world. Post-quantum cryptography exists, the top line, and then you don't need any of these, quantum cryptography. Okay, that's kind of a summary of when. So it's relevant only in some select situations, depending on what you believe and what kind of adversary you want to protect against. Another caveat is there are no standards. It's all proprietary implementations, and it's not tested in the wild. And it could be, and when breaks are found, usually in things like SSL and TLS, they were found because a lot of people were using it and looking at it. And finally, side channels. Only if you're deaf can you be fooled by the BP84 implementation. There are a lot of side channels that are not well understood. People are still working on, attacking implementations, but it's not presumably, these proprietary implementations are not easy to attack and publish results on because they're proprietary. Okay, so the bottom line is QKD is not ready for, like, if somebody is selling you a thing saying, you need to use it today. I think they are overselling. Okay. I'll just very briefly say QKD is just one aspect of quantum cryptography. There are other things you can do. Mentioned quantum mining, which is what Weissman's original motivation was. Delegating quantum computation. You want to do some quantum computation, you send it to a quantum server, but you don't trust them. And maybe you also want privacy. You don't want them to see your data. How do you do it? There's also some notion called device-independent cryptography. You don't trust the devices, can you test them? And things which are kind of classically not possible. If the adversary gave you a device, you cannot trust it as a black box, right? But in the quantum world, they become possible. So that's so there is a lot of very interesting results on those. Okay, to summarize, I think this, okay, don't need the animation anymore. It's just a repetition of what I had in the first slide. So hopefully now you know what post-quantum cryptography is and what quantum cryptography is. And, hopefully you have some idea of why they are useful or not. Okay, that's all I have.
Thank you, Manoj, for this very engaging talk, and thank you specifically for keeping the talk in plain text for those of us who are not cryptographers. We can continue the discussions now. Questions, comments?
We say quantum resistant, does it just mean that the Shor's algorithm cannot break it, or is there more of a criteria for that?
Sorry, I didn't get the question again.
When we call something quantum resistant, do we just mean that Shor's algorithm cannot break it, or is there more of a criteria?
It's a heuristic. It's not just that Shor's algorithms cannot break it, but all the quantum algorithm experts say we can't break it. Then that's quantum resistant as of now. Yeah.
So in BB84, why doesn't Bob send all the reveal cards to Alice? Is there some limitation on the classical channel?
So your question is, in the protocol after reading, why doesn't Bob reveal?
Yeah, why does he choose a random subset? Why can't he send all the...
So the only thing Alice and Bob share is this secret values that Alice on her side encoded into the cards, Bob on his side read them, and hopefully they are the same, or many of them are the same. If Bob reveals everything he has, then there is nothing they're sharing anymore. And it's as good as, just Alice picked her stuff and, so if there is no correlation between what Alice and Bob have, then just by plain communication, they cannot establish a secret key. So this is the reason why information theoretically, if you didn't have the quantum channel, you cannot do.
So the secret key is the set of cards that Bob did not reveal.
The secret key is going to be derived from the values of the set of cards that Bob has read but not revealed. Yeah.
So in QKD, how often new keys are needed? Like, is it based on certain amount of data, which is based on the size of the key? Or once a secure key is established, you can keep using it? Or is there a danger to it? I believe keys are refreshed.
Yeah, so it depends on your, what cryptographic assumptions you're willing to make. If you're willing to make symmetric key cryptography assumptions, right? Then, this little key is all you need forever until, some other reason, like somebody broke into your system or something, right? Yeah, so, or of course, practically you wouldn't keep keys forever. Like say in the internet today, you make a connection, you make a session. At the end of it, you throw away all the ephemeral keys. But yeah, the same key could be used for as long as you want if you believe in symmetric key cryptography. If you don't believe in symmetric key cryptography, so essentially you're in this no crypto world against quantum adversary. You need a lot of, you need to do this QKD. For every bit you want to encrypt, you need one bit of, QKD key, right? Yeah, so those are that's what the, the light blue row at the bottom was saying. That was fine theoretically, but not very practical.
But the current systems which are there available, where do they fall in this?
I think they fall in that little, what I said, the sweet spot.
There it is. Okay, you have written justification.
I have no insight into the actual products that people are selling, but that's, I think, what they'll be doing. Because anything else is less efficient, and you cannot sell something if it's not efficient.
So, nice talk. So, one sort of the underpinnings of you can hear me, right?
Yeah, I can hear you.
Yeah. So, one of the sort of the critical point is the no cloning property of basically if you sort of get the photon here and read it, then you don't have anything to send there, and that's how sort of you ensure the security. Now, but the fact is, since you will have some engineering constraints, you will never be sort of synchronized in your basis for a lack of a better word. And you will have some sort of thresholding mechanism to determine whether you are 0 or 1, or you are red or blue. So technically, you don't need to like clone the wave function exactly. You can sort of have a margin of error, which you have to put in the protocol so that the communication happens. And the same, within the same margin, if you can sort of copy, then you need, then you have sort of.
The trade-off doesn't work that way. I mean, these things, of course, need a much more detailed proof than what I was sketching. But the way the trade-off would work, you can do, for instance, like you said, I don't need to use red or blue. I can use some purple, reader or something, right? I could do other complicated things. But there will be, you cannot get, there will be some uncertainty about one or the other bit, like if you're doing conjugate coding, you talk about. You'll have some uncertainty, and that's essentially enough at the very end when we do privacy amplification. That's good enough. As long as there is enough uncertainty, you'll get a truly uniform or very close to truly uniform key at that. So yeah, you don't need to worry about some information being known about the key, right? So let me say that again. So if you can do that in a way that has zero probability of being detected, then you essentially get no information, right? If you are doing it, or rather, okay. Again, the actual mathematical proof would be different from what I'm saying here, but the fact that you cannot learn it with complete certainty is good enough, for the privacy amplification to give you a good case. That's the bottom.
So, if I understand correctly, you are saying that additional threshold which we are allowing for the actual system to work will be sort of mitigated by the privacy amplification.
I mean, there are these thresholds, right? Not just the honest players are doing something very close to each other. So there is the sender and the receiver have card readers which are very similar to each other. So you need only a small margin. And that's essentially not going to give the adversary anything more than useless information. But there's another point that Sushil was talking about, which is that there are errors in the channel and you cannot afford to abort just seeing one error. But that also, is factored into how you set the thresholds for privacy amplification. So you assume that, okay, there are going to be you're okay with some number of errors. Maybe for all that, all of those errors are because the adversary was tampering or reading things. And still you will be okay if you set the privacy amplification parameters appropriately.
Any other questions, people? Okay, then join me again in thanking Manoj for a very interesting talk. Thank you, Manoj. It was a pleasure to hear you. And I invite Manoj and all the audiences for a coffee in the West End. Thank you for being here. Bye for now. Excuse me. Anybody on Zoom has a question, please raise your hand. Sorry about that. Not in this business anymore. Okay, I'll take that as a no. Thank you. Thank you for coming on Zoom also. Thank you.